Hello everyone, and welcome to a little video looking at some questions from the Chemistry Essentials textbook. We're going to be looking at some stoichiometry problems based on the Analytical Techniques unit. We're going to pay specific attention to question 2.8 and question 2.9 from the textbook. So we're given a bit of information here, and what we're told is that 2.00 grams of zinc metal was added to 100 milliliters of 0.10 mole per liter copper nitrate solution. We're given the chemical equation for this reaction, and we're asked to determine which product is in excess and by how much. So we can see we have our two products there. We have zinc and we have copper nitrate, and we're given the information for those two in the question there. Now first off, we're looking at zinc metal, so if we want to calculate the number of moles, which is obviously going to be handy when we're answering that question there, we're going to need to look at the solid formula for actually calculating number of moles, not the solution formula. So we're going to be looking at N equals little m, which is the mass, over big M, which is the molar mass. As a result, we can calculate the number of moles of zinc by just being given the actual weight of the zinc metal in the question. So in this case, we see that the number of moles is equal to 2.00 on the molar mass, which we can read off the periodic table as being 65.38 grams per mole. From that, we find that the number of moles is equal to 3.06 times 10 to the negative 2. We do a similar thing again with the copper nitrate. However, this time we know that we're obviously going to be looking at the solution formula, because we're told in the question that copper nitrate is going to be in solution form, aqueous form. So as a result, we take the concentration, which we know to be 0.1 moles per liter. Again, it's in the correct unit, so we can just substitute it straight into the formula. And we need to multiply by the volume. And in this case, the volume is given in milliliters, not liters, so we need to do a quick conversion. Luckily, it should be pretty straightforward to work out that if we have 100 milliliters, we simply have 0.1 liters. Multiplying those two together, we get 1.00 times 10 to the negative 2 moles. So just by looking at those two, we can see that zinc is in excess, and as a result we can work out the difference in the number of moles between the two, and we can work out essentially by how much zinc is in excess. So we take the 3.06 times 10 to the negative 2, which is the number of moles of zinc that we actually have, and we take away or subtract the copper nitrate number of moles that we have for the copper nitrate solution, which is 1.0 times 10 to the negative 2. And as a result, we actually see that we have 2.1 times 10 to the negative 2 moles of excess zinc metal. So it's just a matter of being able to use the two key stoichiometry formulae there. Again, we use the one for the solid zinc metal, and we use another one for the copper nitrate solution. All the other information is given in the question. It's just a matter of being able to identify which one is a limiting reagent. And in this case, the limiting reagent is the copper nitrate, because it has the lower number of moles. So therefore zinc is in excess, because that's the other one. So now we're asked to calculate the number of moles of zinc nitrate formed, and hence calculate the concentration of zinc nitrate in moles per liter in the solution at the end of the reaction. So using our product and reactant theory before, we found that the number of moles for our limiting reagent was 1 times 10 to the negative 2 moles. So hence we know this is the number of moles that we're going to have of zinc nitrate formed. Again, just by considering copper nitrate as the limiting reagent and the number of moles actually reacting. And again, if we look at zinc nitrate, we can see that it's zinc and then our nitrate. So what we can actually get from this is we can read the question and interpolate that we're actually looking at a solution as the product here. So we need to use the N equals CV formula. So we have number of moles equaling the concentration times the volume. So we know the number of moles because of our limiting reagent on the previous slide, which is obviously the copper nitrate. And then from there we can substitute that into the equation. And we know what the volume is going to be. It's going to be the volume that we had for the copper nitrate on the previous slide too. So it's 1 times 10 to the negative 2, equals 0.1 lots of C. And then we can rearrange to find C, which is the concentration. And we find that the concentration is equal to 1 times 10 to the negative 1 moles per litre for the zinc nitrate at the end of the reaction. So now we're asked to calculate the mass of copper metal formed. Again, we're looking at copper metal, so that indicates that we need to look at the solid formula. And to calculate the mass, we're going to look for the little m. So we know the number of moles is 1 times 10 to the negative 2, because that was our limiting reagent before. That's the number of moles that we actually had that reacted. So as a result, we can also determine the molar mass of copper from the periodic table. In this case, it is 63.55 grams per mole, and we substitute this into the equation. We then rearrange, and we find that the mass is equal to 6.4 times 10 to the negative 1 grams, to two significant figures. So now on to the next question. And in this question, we're given that we have 50.0 milliliters of a solution, and it contains 15.0 grams of dissolved copper chloride, CuCl2. And it was mixed with 50.0 milliliters of a solution containing 12.0 grams of dissolved sodium hydroxide, NaOH. And we're given the chemical formula below, the chemical equation. So we can see that sodium hydroxide and copper chloride are our reactants, and we can see our products on the right-hand side of the equation there. And we're asked to calculate the mass of the copper hydroxide precipitate formed. So precipitate indicates solid, and from there we can also see that the copper hydroxide is the first product on the right-hand side. So now what we can actually do is calculate what's happening with our reactants. So we're looking at copper chloride first. And again, it's copper chloride being dissolved in a certain volume. So we're going to need to look at the solid formula first. So we have N equals the little m, which is the mass, on the molar mass. Again, we use this because we have a weight given in the equation. We're given 15.0 grams of copper chloride. And we can work out the molar mass of copper chloride from the periodic table. We just find the sum of the copper's molar mass, and then we have two lots of chlorine's molar mass. It's just a simple matter of looking them up and actually summing them together. And then by actually performing the arithmetic there, we find that we have the number of moles equal to 1.116 times 10 to the negative 1 for our copper chloride. So then for our sodium hydroxide, we are going to repeat a very similar process. We're going to substitute the mass in as 12 grams, and the molar mass is going to be equal to simply the sum of the molar masses of each of the individual atoms that we have there. So we have Na plus O plus H. And doing the arithmetic, we find that that's 3.0 times 10 to the negative 1 moles. So the amount of precipitate formed is 1.116 times 10 to the negative 1 moles, because that is evidently the lower number we have out of the two there. And I just noticed a mistake, that there should be NaOH. I apologize for that. And then from that, we can actually substitute in the number of moles that we found from our limiting reagent, and then we can substitute in the molar mass of the copper hydroxide. Again, it's a precipitate, so we're looking at a solid. So we rearrange the equation to find the mass, and we find that the mass of the copper hydroxide precipitate is going to be equal to 10.9 grams. So now we're asked to calculate the concentration of sodium chloride in moles per litre in the solution at the end of the reaction. Now, if we look at the mole ratio, we can see that the stoichiometry coefficient for the copper chloride is 1, and the stoichiometry coefficient for the sodium chloride is 2. As a result, we can actually say, well, 2 times the limiting factor of NaCl is produced from this reaction. Again, it's essentially just looking at a simple mole ratio, considering what is formed, what is actually used, and what's produced. So from this, we can work out the number of moles of NaCl formed, and the number of moles is simply going to be 2 lots of the number of moles of the limiting reagent, and we're going to get 0.2 2.32 moles from that. Then we can use N equals CV formula because we know that we're going to have sodium chloride there, and it's going to be in a solution form. And the volume is simply going to be the sum of the two volumes that we have before. So we had 50 milliliters and 50 milliliters. So we know that the volume in which this sodium chloride will be in is going to be 100 milliliters, which converts to 0.1 liters. As a result, we can rearrange the equation, and we should find that the concentration is equal to 2.32 moles per liter when we're rounding to three significant figures. Hopefully this video was useful, going through question 2.8 and 2.9. Thank you for listening.